Thank you.
Okay. All right, I think we can move forward. Okay, so we put the ABC of the continuous wavelet transform, but then what happens when you move to the discrete space? And actually, we were working in a discrete space because what I gave in input was a discrete signal, right? Well, in the discrete space, we actually don't need to oversample your signal. Indeed, what we might aim to do, it's something similar to the discrete Fourier transform, where you go from a base where you have n samples and you have n coefficients. And with wavelet, we might aim to do the same thing. So we want to define a base which has the same dimensionality of our original data. So this is done typically by putting some constraints of our parameters. So while before we let A and B span with certain freedom, what we do in the discrete transform is to build a function in such a way that the scaling and the shifting are, say, linked to integer scaling and integer translations. Okay, so we actually define an A0, which is in most of the cases is 2. So we scale by factor 2 every time. And the translation, so say we have binary relations, what I referred before as voices or octaves, and then you have translations, which are again multiples of 2. So if you think about it, you have something like this. So when you select m equal to 1, for instance, then, or say equal to 0, let's go to the lowest level, then this is 1, and what you get is actually the mother wavelet, which is sampling exactly at integer steps. When you go to the next level, so we set m equal to 1, what you're doing is amplifying your wavelet, so you're making, say, let's say you're making it wider. And in that case, since it is wider, it makes no sense to sample at the same interval. So what you do is actually translates by factor of 2. And then you keep going, and what you get is that for the large scales, then you have spacing that goes, say, with the powers of 2 of m. So this is the discrete wavelet transform. I'm putting it there as integral, but actually you can easily write it as discrete sum. And among this family of wavelets, actually we can select many different wavelets there, but we search for very special ones. And we typically seek for orthogonal wavelets. Why? Because we want to build a basis, right? So we want to move to a different representation where we have, say, n components in that base. So we seek for wavelets which are mutually orthogonal. And the nice thing is that if they span the entire space of the function, so imagine they span L2 of R, you can take whichever function and you can find it as, you can write it as a weighted sum, a linear combination of those wavelets. Okay, so it's just a representation of the base. Okay? So how do you get these families? Well, if you go on the lecture notes, there is a mathematical derivation, and actually it's a very short one. You'd better go to the book of Malat to find a more insightful derivation and more proofs. I want to give you the basic idea, okay? So I'm using an example. How do we build, for instance, the R wavelet? Imagine that we have a signal like this. So this is a generic function in L2, okay? Actually, we can discretize it. So suppose it's a discrete set of measurements. And then suppose that I want to create what is called an approximation at a certain level of resolution. So imagine that you have a sensor which is able to, let's say, average your function over a finite interval. This function, it's a scaling function, what we will call in a moment father wavelet. I can select it, for instance, as a function which has uniform value in each interval n plus 1. So for instance, phi 0, 0 is the function that has constant value between 0 and 1. Okay? If I do that, I'm just thinking of a sensor which takes the value of the function here, okay, and put the average value on that interval. So I take an approximation of xt as a bunch of these steps, okay? This one is the approximation at this level. So I'm going away from a moment from the space of L2, I'm going to a space which is defined by this interval function and has approximation of this kind. So it's a space where all functions are sort of stepwise functions. I can do the same trick at another resolution level, a higher resolution one, in which instead of taking these functions, I make the approximation with a function that is, say, narrower. So in this case, a function which is, say, if I take phi 1, 0, it's a function which is equal to 1 only between 0 and 1/2. Okay? Of course, this guy here can be written as two of these guys, okay, one to each other. So in a certain sense, the space of this function is included inside the space of this one. It's nested inside. Okay? So these are two different levels of approximation at two scales which are, say, defined as factors of 2, one between each other, just as we were saying before. The curious thing is that if I take the difference in between them, so if I just make f1 minus f2, it looks like a whole bunch of Haar wavelets. So you see here, this is the Haar wavelet. So it's like the Haar wavelet is descending from this choice of the scaling function, the way I'm filtering. And I could actually write the difference in between the two as a linear combination of the Haar wavelet with interval width equal to 1. Okay? So in a certain sense, we get to what Miguel was referring at some point. I could take a function at a certain resolution level, and I could write it as the sum of an approximation at a lower resolution plus some details. This approximation is a linear combination of the scaling function, the phi. This detail can be written as the linear combination of wavelets, okay? And I actually can play the trick also for f1. So imagine that I take this, I go to the next resolution level, so I'm making my scaling function thinner and thinner, and what I get is that this f2 is f1 plus wavelets of smaller interval, 1/2. And I can keep going up to the level of resolution that I want. Ideal, I can go up to the sampling rate of my function. So practically, I can write my function defining a level 0 as the sum, the weighted sum of the approximation function. So this guy here depends on where you put your base level, let's say your low-pass filtered version of the signal, plus a whole bunch of wavelets at different resolution levels. These are what are called details. So a bit more formally, but not much more. How do I construct the multi-resolution analysis? That case was for the Haar wavelet, but I could select whichever scaling function. It doesn't have to be uniform. I can select a different one and get another wavelet. So if I want to create what is called the multi-resolution analysis, what do I need? I need a sequence of subspaces, okay? V0 was the one containing the f0, the function that was constant in intervals of width 1. V1 is the next level resolution, and so on and so forth. I need to select a scaling function called father wavelet. Then I need an equation to write this scaling function in the different subspaces. It's called refinement of two-scale equation. Again, I'm skipping the demonstration. It's just a way to relate all the approximation at all levels as a linear combination of that at the lower level. And then finally, I need the mother wavelet. Again, we saw it in the heuristic way. You can demonstrate that if you want to create a function that is orthogonal to the scaling function, the same resolution, you can play a cheap trick, and you can write it as a function of the coefficients building the scaling function in some way. So I'm skipping the deformation. Just know that this is orthogonal to this. So say practically, this is describing the part that is dropped by the approximation. Okay, so it's the detail that is missing to the approximation. The way this is implemented practically is in a very efficient way using filter banks. And this operation is of order n, so it's very efficient. The idea is the following. Imagine that you have a signal which has a set of n samples, and you want to decompose it at lower levels. So what you can do is to make it pass through a high-pass filter and a low-pass filter. So this H is the high pass, this G is the low pass filter. And then what you do is to take this high pass stuff and you store it somewhere, okay? And when you do it, you don't sample by factor of 2, because actually at the time of filtering, think of the Haar wavelet. When you filter on a scale, then what you're doing is changing Nyquist in a certain sense. You cannot get details that are smaller than a scaling function. So what you do is throwing this, say, downsampling your signal. This one is what you get after filtering with the scaling function. It's a low-pass filter, okay? So this is your approximation at the next level. if you want to move forward, well, actually already at this stage, what you could do is to write H0 as the sum of the low-pass filtered plus the high-pass filtered. But then you can keep going forward. Now your number of samples has halved. And then what you can do is make it pass again through the same high-pass and low-pass filters. And you obtain a new set of details, which now are shorter. Okay, so imagine that this was 512, for example. This is 256. And the next level approximation, again, you can keep iterating, okay, until you don't get to the lowest level. So this is the way this is implemented. And of course, the choice of filters, Miguel will discuss, I think, this afternoon about that, okay? Or we already mentioned something in this class before. So imagine that you have a signal like this, and you want to decompose using the discrete wavelet transform. Then this is a 4-level discretization. After I make it pass through this set of high and low pass filter, and I store at each step what comes out from the high pass filter, I arrive at the lowest level with what is called the approximation. And then I have the details at all levels. And if you look at the amplitude, you see that they are typically decaying. This is some feature that is normally exploited when you do wavelet filtering. You take the details with less intensity, you throw them out, okay? You chop them from the reconstruction, and you get a signal which contains the most important stuff. If you put all of them together, you see that we moved from a 512 signal, which is this one, to a 512 set of wavelet coefficients, when this is the approximation. And you see, since there is quite some low frequency carrier, we saw it into the approximation, and then you have the details of all levels, and you see that these are actually quite irrelevant. In principle, you can throw them out and clean this signal the same way you will clean it using the Fourier transform. Okay, so to close, let me show the second tutorial. We have actually in the room, I still haven't had the opportunity to shake hands with Nan Deng. This test case is from the group of Bernoak, is the fluidic pinball. So you have a set of these 3 cylinders. In this tutorial, we're actually really not interested much in the fluid mechanics, okay? But we are more focused about on properties about filtering and compressing using the wavelet transform. So what I'll do is to take the field, put some noise, okay, and start to extract features in some way. Sure. I can send you a presentation if you want. Okay, so this is the original signal. I will not go through the code. It's actually very simple because it uses very compact functions that you find in the wavelet toolbox in MATLAB, and also in Python there are equivalent functions. So what I do is to take the streamwise velocity, and I introduce some noise, right? Very simply some Gaussianly distributed random noise. If I take the first level discretization, so I'm just making the first octave, well, this is done in which way? While for 1D signal, I just needed to filter with the scaling function and get details, and so I obtained a plot of vectors, a plot of data. Well, in this case, I actually need to do it in 2D. So in the end, well, my scaling function, instead of being 1, 1, it would be, say, a square of 1s. And this gives a low-pass filtered version of your signal. This is done, by the way, with the R wavelet. And at the lowest level instead, well, I have several options for the wavelet. One is a function combining, say, psi for the x direction and psi for the y direction. So it's sort of, say, diagonal detail. Another one is psi for the horizontal details times phi, and that is still orthogonal to this. So it's nice to isolate horizontal details, and I can do the same for the vertical details. Okay, so I need to find, say, to seek, in this case, the 3 opportunities I have to build functions that are orthogonal to the approximation function, and so that allow to obtain all the details that are missing when I filter out here. If I go to the second level, so what I'm doing is taking the approximation, what you found in this first square up here, and say further filter. So now I have the details at the second level, and you see that while this was noise dominated, I start seeing here some features, some horizontal hedges that are those coming out from the shear layers here, okay? Notice that here what I did, if you look at MATLAB code, I actually rescaled all these so that they are at 8-bit levels, but actually these details are much weaker than what you find here. So in principle, what you can do is to make a decomposition and throw out the stuff that is irrelevant. So this is what you get. And actually, I think here it probably makes sense to open quickly the MATLAB code. Let's quit debugging here. So this is where I put the noise. This is the decomposition I used just for purposes of demonstration. And then later, what I do is to use a fourth-order Dobeschi wavelet to create a 4-level discretization. So how do I perform the thresholding to get rid of the noise? Well, what I do is to sort the absolute value of the coefficients, okay, and then decide which is the fraction to maintain. This is actually a tough decision. In this case, I just put a number, but in principle, this decision is normally taken considering the amount of noise you estimate in your signal. There are many ways of doing it. There is the universal scaling. There are interesting papers from Donald Johnson in the 90s. So there are ways to make this selection in a wiser way that I did. Okay. But anyway, let's live with the 2% being fine. And then what I do is just to maintain the largest coefficients. Okay. So let's go back here. There you go. So indeed, after filtering with the wavelet, I see that I retain most of the features. I actually make a quiet job in cleaning. And what I'm putting here is what I get if I use a standard filter in the Fourier domain by retaining the same amount of coefficients, so the same 2%. This doesn't have to be necessarily fair, okay? Maybe in the Fourier domain, I might need less coefficient. And actually, this is one of the cases where the features are quite smooth, and Fourier normally does a good job. Nonetheless, here you see that there are some residual of the noise, so I might be more aggressive here, which might mean that I might lose some more feature of my signal. So with this, I conclude. I hope I gave you at least the basic idea that is needed for this afternoon to work with filter banks and wavelets and try to understand what is behind the multi-resolution POD. And let's see if you find some interesting application in your future to use wavelets. And now we have some time for questions. So please go ahead. Where do you see the wavelets in 20 years?
Something like that. So, for instance, for the cylinder work, you could use, at the moment you are doing a Fourier transform, you assume something like you have a ergodic behavior. So you are going back to your original data point at some periods.
Yes. And that's what you see.
And if this is the case, so this is a classical example for ergodic behavior. So at this point, you should not throw away the past data. To some extent, the past data can be used to reconstruct this and set a bias to your filter to being closer to what you have recorded in the past.
Yeah,
and you are now presenting tools which you can use if you don't have this ergodicity.
I agree.
And would you have an idea where you could make the switch? So you look at the data and do you have an idea where you can push the switch to say if you are, should use your past data, or where you have something new and you need more generic tools for the filtering?
I actually haven't thought about it. As an experimentalist, I don't used to have time resolution in my PIV measurements, so I really can't use easily the information I have before. Okay. Especially low Reynolds number, high Reynolds number, you don't have that thing available. In principle, when you do, yes, it might make good sense to use that time information. Normally in experiment, what we do is just to apply Fourier also in time. So you say you combine time and space. That is the dummiest thing you can do, but normally works quite well when you have random noise. But then I agree, you can build, say, better tools to do this scale-wise, so say sort of enforcing also the persistency of scale if you want to track down the stuff that is active and the stuff that is not. Yeah.
If you really believe in agrodicity, you can take the POD and essentially use an autoencoder
Yes.
from the data, do POD, and then you have the same results. And
I think this guy is going to. We are spoiling Andrea.
Okay.
This guy is going to talk about this afternoon. But yes.
The next thing, the autoencoder uses all the data. You can also use the temporal coherency, and then you have a second layer. So you have to do these things for the online extraction of a phase from flow visualization. So if you want to do control based on flow visualization, you have to use both type of.
This is a very nice idea, actually. Yeah. Thank you.
Are there any other questions? Well, then if not, we thank again Professor Discetti for this excellent introduction.
Okay.